All right, welcome back, Cal 2. I'm going to teach you a little bit in 9.6, but before I do, I'm trying to summarize some things here. So in section 9.2, we started talking about infinite series, and we've got all these tests to determine whether they converge or diverge. It's a big chapter-long project. Anyway, back in 9.2, we had what was the nth term test, or I call it the divergence test sometimes. Do you remember what that one was? That's a good one. You take the limit of the nth term. If it's not 0, the series diverges. Stop. So what I always cautioned you about is, well, what if you take the limit and it is 0? Does that mean it converges? And the answer is no. Nobody said that. And we've learned, though, that a lot of times when if you take the limit and it's not 0, it diverges, is what the nth term says. If you take the limit and you do get 0, it's got a chance to converge, but you better explore some other test. So it depends on how fast it's going to 0. It's interesting. Anyway, we also did a sequence of partial sums. I did one of those before the break. They're kind of long and complicated. Those were telescoping series is what they were. Or it's good to do a sequence of partial sums on a telescoping series. Makes it doable. We looked at geometric series in pretty good detail. They're easy to spot and easy to tell whether they converge or diverge. We just looked at an integral test, and then a p-series test. So these are all tests to determine whether a series converges or diverges. Listen, I'm skipping a couple sections in 9.4 and 9.5. There's some comparison tests that are okay, and there's an alternating series test that's interesting, but I'm skipping those. I'm getting to 9.6 where these tests stop here. This is the last one. Actually, there's one other one. In 9.6, there's something called the root test. I'm skipping that one. So I've skipped a few. I think we got a long enough list of tests. But I want to do the ratio test. So here we go. If I've got a series in 9.6, the ratio test says this. You take the limit as n goes to infinity of this ratio of the nth plus 1 term over the nth term. And here's the conclusion. If this limit comes out to be less than 1, the series converges. If it's greater than 1, it diverges. If it equals 1, it's inconclusive. Maybe you better go do another test. So that's the ratio test. It's a pretty good one. But I'm going to say this. It works well. I want to say this. It works well for powers of n, and n factorials. So it works well when we see those. It might work well for something else, but it works real well for those. So I want to do an example. And look what I'm going to do. I'm going to do this 3 to the n over n factorial as n goes from 1 to infinity. So this is my example. It does have powers of n, and it also has some factorial in it. So it should be a good candidate for the ratio test. I'd like to point out that no other test really works. Let me try something here. Let's try the nth term test. If I take the limit as n goes to infinity, just trying to do the good old nth term test, I get infinity over infinity. I can't do L'Hopital's rule very well. I could argue that the factorial beats the exponential function to infinity. I mean, exponential functions go to infinity quick, but I think factorials beat them. Anyway, that would argue that the denominator gets to infinity quicker. That would argue that this goes to 0, and I know nothing, except it's got a chance to converge. Do you want to do a sequence of partial sums? No, you don't. No, it's not a geometric series. Do you want to do an integral test? Anybody? No, you don't. It's not a p-series. Okay, well, let's try a ratio test. Here we go. The ratio test says take the limit as n goes to infinity. Watch this. They do put absolute value on here. It's the nth plus 1 term. So that's 3. You substitute n plus 1 for all the n's over n plus 1 factorial divided by the nth term. The nth term is staring right at me. It's 3 to the n over n factorial. So this is the limit I'm trying to do as n goes to infinity for a ratio test. Of course, almost immediately, and in future problems I tend to just do this automatically. Instead of dividing by this nth term, I want to flip this up. I want to multiply by the reciprocal of the nth term. So I end up multiplying by n factorial over 3 to the n. Okay, that's the limit as n goes to infinity. So maybe you can tell what's going to happen here. Listen, I have n factorial over n plus 1 factorial. We did a little work. We practiced. That should cancel. You know, n plus 1 factorial is n plus 1 times n on down to 1. N factorial is n times blah, blah, all the way down to 1. So n factorial cancels with the n factorial here, leaving me with an n plus 1 in the denominator. What about these 3's? I got 3 to the n plus 1, and I got 3 to the n. They're going to cancel. I've got 1 extra 3 in the numerator. So I think they cancel. Sometimes students have a hard time understanding that. You know, maybe there's 100 3's here, 3 to the 100th. Well, that makes this 3 to the 99th. So they cancel. I'm left with 1 3 in the numerator. So this is the limit of the nth plus 1 term over the nth term. You flip this up. The reason it works well for powers of n and n factorials is because the way they cancel each other. And so we're left with this limit, and that's not difficult at all. As n goes to infinity, it's 3 over infinity. The answer is 0. The answer to that limit is 0. When the answer is 0, that's less than 1, it converges. So this series converges by the ratio test. Again, that's kind of the way I want you to talk and explain it to me. Even though you showed me your work, it does look like you did a ratio test. I want you to talk to me and say, okay, the answer was 0, that's less than 1, it converges by the ratio test. Thank you very much. The rest of this chapter is some different area, different stuff. So we need to pause and practice all this stuff to tell whether a series converges or diverges with these tests. I skipped a few to trim this down a little bit. That's okay. It'll be all right. And so keep working hard. I appreciate it.